Well, good afternoon, everybody, and welcome to the last of today's webinars from Smart Vision Europe. I'm Charles Quinn. I'm an analytics consultant at Smart Vision Europe. I'm joined online today by my colleague Rachel. And the topic of the last presentation today is about using SPSS statistics for marketing applications. Um, if you haven't joined any of these sessions before, you should be aware that we do record them. So you'll be able to listen to a recording of it afterwards. And there's some slideware here, so you'll be emailed out a link to download the materials after the session is ended. And if you think it's particularly relevant for colleagues who are unable to attend today and you can get enough of them together, then we may be able to arrange a rerun of it. The best thing to do is just drop us a line. Now, with regard to asking questions, we ask you to use the chat panel because all the lines are muted. And if we run out of time, we'll obviously follow up with you offline. If you don't know who we are a technology company. We're actually a gold accredited partner to IBM, as well as a company called Predictive Solutions and Data Robot. And we specialize in data science, statistics, advanced analytics technologies. Although we do work with open source technologies such as R and Python, etc. And we're a relatively small organization, but we're made up of a team of people who all have very deep long-standing experience going back 30, 35 years working in the advanced and, and predictive analytics um, uh, technology sector, I guess, software companies like SPSS and SAS and IBM. It means we've got a lot of deep experience applying analytical techniques and analytical applications across many different sectors, marketing being a typical application that we would have employed and worked within on many occasions across both the for-profit and not-for-profit sector. We're going to start off today. We've basically got a smorgasbord of different procedures we're going to look at. And I thought a useful one to look at is a typical problem that people have all the time, which is just basically performing A/B testing, and how can we do that and how can we do it in such a way that we are confident that we'll be able to detect an effect if an effect actually exists there. So, as you're probably aware, A/B testing really refers to the idea that you've got, uh, in most occasions, two different offers or two different creatives, and you wish to compare their performance. So, known as split testing, it's a method used to compare two versions, for example, of a web page or an email or an app feature or other content, see which one performs better. And the process involves randomly showing two different versions, A and B, to different segments of users and measuring the responses based on predefined metrics like click-through rates or conversions or other user interactions. Now, analysts often have to think about how much data they need to collect in order to see if a change has an effect. This is especially true when you're dealing with behaviors that only occur a small percentage of the time, such as a conversion, i.e., when someone actually buys something or when someone actually subscribes to, I don't know, a mailing list or subscribes to a newsletter or to a service. And A/B testing helps businesses make data-driven decisions to optimize their content and therefore improve user experience. So in our little example here, we have a Smart Vision newsletter that we send out and people can subscribe to it. And currently, the button that is used is simply marked sign up. And let's say there was an argument that that was a bit perfunctory and not terribly warm. Somebody said, well, how about we just go for something a bit softer and just have something like keep me informed as a little button? That could be our test button. Would one creative or the other, would it actually lead to, a higher sign up rate or higher subscription rate for that particular newsletter or that service that you're providing? Now, the issue here is that if you want to do a statistical test for this, you've gone out and you've collected the data. So let's say you've exposed the test button in a mail shot to only a relatively small proportion of people in your sample. Let's say only 10%. You don't want to change everything. You just want to gather enough data, get enough responses to see if it makes a difference. If you want to do that, it's pretty easy to do a statistical test. It's really easy to do. There's lots of statistical tests out there that would do that. A typical one would be something like Fisher's exact test, something like that. And with any sort of significance test, you're looking for, a significant result, which would usually be marked by a p-value that was less than 0.05. But one of the things that people don't really realize is that often you're dealing with, first of all, you're trying to deal with a minority of cases where people will actually click on these buttons. So, if you've got 10,000 people you're sending it out to, you might only find that only 500 out of those 10,000 actually click up on it, click on one of those buttons to begin with. So then you're comparing a sample of 500 to another sample of 500. And you might only be trying to detect really small differences, maybe just a few percent bias towards one group or the next. And that presents a problem from a statistical standpoint because most statistical tests may not be powerful enough to detect those differences, if they're very small differences, very subtle differences between, one email creative and another email creative, or one coloration from another coloration, or whatever way you're splitting up your or designing your little experiment, your A/B test, that the differences might be so small that they can't really detect them. In which case, you may have to perform something like a power analysis, which is what we're going to do, which will tell us how big a sample size we would need to have in both of these groups in order to stand a chance of being able to detect those differences. In other words, if you were trying to test whether or not a coin was biased or not, let's say somebody said to you that they think a 50p coin is more likely to come up heads than, I don't know, a 10 pence coin or something like that, or a pound coin. Um, you know, you couldn't just test that by flipping each coin 10 times, obviously, because you might be looking for a very, very subtle difference. You're going to flip it a lot of times, at least 1,000 times each, really, to see if there's a difference in the heads to tails rate in across the two coins. In which case, you might want to try to estimate or calculate how big the sample size would be in order for you to stand the chance of detecting it. And as I say, this is known as power analysis. So I'm going to jump out to a data set here. Here's our little data set. It's called A/B testing. And here we have two key variables here. We have A/B test group, which is our two creatives. One is simply the control, that which is labeled sign up, and one is the test, the new one, which is labeled keep me informed. And you can see that the control is about 90% of the data, 89% of the data thereabouts, and the test is about 11% of the data. There's 41,000 examples of the test being serviced, being provided or surfaced to people. Um, and 329,000 examples of control being surfaced to people. So, and this is actually stretching back over 3 months. So you could even go further and say, well, let's do some analysis here and get into sort of deeper analysis and say, okay, let's look at the test broken down by the month that they were put in, and we could put in like row percentages and stuff like that and see how that breaks down. Then we've got control and sign up. Oh, actually, we haven't added. Oh, we have it in percentages here. So we can see that December is a big month. 42% of the control group has been surfaced in December, and 42% of the test group's been surfaced in December. So you got some variability. You got some other factors there. You got other things like, the browser that you're using, and does one type of browser perform better than another type of browser? So these are typically what you would have, but critically, what you have is this key this key response button, which is, did they click subscribe or not? And when we click on that, you can see that only 5.8% of people overall click subscribe. So let's just go and look at the differences here. So if we look at A/B test and we look at subscribe, and then we change the percentages. No, that's all right. I can keep the percentages on row percent, I think. If I click OK at that point, let's just look at the difference. So 5.9% of the people using the control hit subscribe compared to 5.3% of people using the test. So it does look like the test keep me informed, if anything, has a lower subscription rate than the current control, the current method, which is just a button marked sign up. So that's you might think to yourself, well, that's the end of that. But then again, you might say, well, maybe they're exactly the same. Maybe these type there's only a very small difference here of 0.6% or so. If it was the other way round, how big a sample size would we need to to stand a chance of detecting this difference? Assuming there is a statistical difference here, which we haven't run a stats test yet. Well, maybe before we did the test, if we knew a few things and we knew how much data to collect, and we had a rough idea of what how small a difference one method might choose over the other, we could go to analyzing and go to power analysis, and that would help us estimate a sample size. So power analysis is where I go down to proportions here. It's a proportion test. It's an independent samples binomial test. That means that there's two groups and they're independent of one another. And what you normally do is you choose a power value. Now, when we're accepting or rejecting a null hypothesis in tools like SPSS or other statistical analyses, we usually work at a value of 0.05. So the probability has to be less than 0.05 for us to reject the null hypothesis. With power analysis, you're doing something completely different. With power analysis, what you're saying is, assuming an effect exists there, how big a sample size do I need to have in order to stand a certain chance of finding the effect if it existed? And I've actually done work for companies where, they just can't they can see the numbers are slightly different, that using the new creative is slightly different, but the probability values when they do a statistical test aren't showing that it makes a difference. And I've been able to demonstrate to them the reason why that is because the tests don't have enough power. And they don't have enough power because of the nature of the data. The sample size isn't big enough, something like that, and they'll have to wait a bit longer. Now, the threshold, the sort of standard threshold that people choose is actually zero point 0.8. And zero point 0.8 means 80% power. That means if I run this test and there is an effect, I want whatever test I'm going to run to have an 80% chance of finding the effect if it exists. In exactly the same way that if I did a statistical test and I only flipped the coin 10 times each, for the pound coin and the 50p coin, that would have very, very little power. You'd stand very, very little chance of finding an effect if it existed with a sample size that big. So this is a similar sort of thing. We want an 80% chance. Now, in fact, you can actually set it higher. And I'm going to, just for argument's sake here, show that you can set it to zero point 0.8, which is 80% chance. And I can also set it to zero point 0.9 to have a 90% chance. And I can set it to 0.95 and so forth. So I'll just do those two to begin with. You can actually set a range of values. And now what I could do is say, what's the group size ratio? Well, if it's one, it indicates that they're exactly the same. They're the same size, that they're equal portions. We know that they're not equal portions. We know that the smaller group size is only 10% of the larger group size. So the test group is only 10% compared to the control group. It's only 11% or thereabouts. And then we have the proportion parameters for one group. Well, I'm going to assume that, let's say, just for argument's sake, that we have a 0.55 chance. This is not clicking on here. Hold on a second to see if this works. Let's see if I got 0.55. No, it's not responding. Let me hit cancel, do it again. Call it up. No, wrong one. This froze on me there. We'll do it one more time. Is that, oh, here we go. So it's come back 0.55. Let's say zero point 0.5 and 0.55. So actually, that would be 50% and 55%. It's not that. It's 5% and 5.5%. So these are proportions, not percentages. So this is how small a difference I'm looking for. I'm looking for a difference between a 5% response rate and a 5.5% response rate. And I'm asking it to set a significance level for my statistical test at 5%. And I'm going to run what's called a Fisher's exact test because that's just a really good test to use when you got what's called a 2x2 crosstab. You've got two categories in the rows and two categories in the columns, which is what we got here. And if I click OK at that point, it gives me a result and it says, look, if you want 80% power, if you want an 80% chance of the test being able to find an effect, assuming one exists. Then one group needs to be the large group needs to have at least 300 and 31,617 in it, and the second group needs to have 31,617 as well. I think I've got that wrong. I think I need to do that again because yeah, the group size ratio needs to be set to zero point 0.1. I lost that. Let's click OK. There we go. So look, saying now it's 10% and 90% appropriate, respectively. So it's actually saying you need a group size. In one group, the large group needs to have at least 173,000 cases, and the other one needs to have at least 17,000 cases. And if you wanted 90% power, then one group would have to have 232,000 cases, and the other group would have to have 23,000 cases. Now, we can see from looking at this that this actually has 329,000 cases in this control group, and this group over here has what was it? It's actually, yeah, it's 349,000 versus 21,000. That's the group sizes we got across the nose and the yeses. So we stand a pretty good chance of finding this effect. We're well above our level of power that we need. Even we could even get to 90% power. Let's go back to the crosstabs here and run the test now. If I go to statistics, I can ask for a chi-square test. The chi-square test will include a Fisher's exact test. If I click OK at that point, there's the Fisher's exact test. In fact, all the test results show them to be significant. If we look at a one-sided exact test, a one-sided exact test would be if you expected one group to be bigger than the other. It really doesn't matter. It's more conservative. But if you said, I just expect there to be a difference, it could be could be the control is bigger than the test, or the test is bigger than the control, a difference in either direction. Really doesn't matter. They're both statistically significant. So it's saying that, yeah, it's saying effectively that the control is better than the test, even though it's a really small difference here, 5.9% versus 5.3%. That is statistically significant, and you really should stick with the control group on that. So that's an example of you doing an A/B test using Fisher's exact test through a crosstab, but using the power analysis procedure, which is under up here under the analyze menu, to to find out how many records you would need to collect in order for the test to stand a good chance of finding an effect, assuming it existed. Okay, so that's the first one, A/B test or the applications for marketing. What else can we do? What about segmentation and recency frequency monetary analysis? We have both different types of segmentation analysis. So how are your customers or are your clients characterized? Do you impose your own classification upon them? Are they classified by region, by the value that the money they spend, by the products that services that they use? Are they clients in a public sector situation? Are they different types of students? Grown-up students and younger students? Are the people doing different types of making use of different types of services? Normally, organizations already have some sort of classification for their clients or their customers. What we're talking about here is using the data to actually tell you what different types of customers or clients you've got there, and that's known as segmentation. So the idea being that the data will suggest groups to you, and that using techniques like cluster analysis, you can uncover subtle differences in these previously hidden groups, and thus be able to interact with them more appropriately because the data reflects the fact that they behave in a different way, or that they are somehow distinct from one another. And as a result of that, you get a lot of companies creating segmentation schemes, and they have names, little nicknames for different customers. In fact, sometimes that's one of the harder parts of this process. This process is something more of an art than a science, I would say. A lot of people would argue that. There's no single one solution to it, but you've really got to look at some of the results and think of whether or not they make sense. So you might have, ad hoc big buyers, people who come in and spent a lot of money, but they don't do it very often. You get people who are very loyal, but they kind of sitting in the background making small purchases. You get, endangered exotics. You get DND, do not disturb, people you should leave alone, or cautious spenders. This is typical of the sorts of labels that people would give. Now, cluster analysis is known as an unsupervised technique. It's unsupervised because we're not trying to predict an outcome. We haven't got a target variable here that we're trying to predict. We're simply saying, okay, go off, look at the data, and see if you can form as much as possible homogeneous groups within that data, groups which are distinct and different from one another. So that can be tricky, but we'll have a little look at how we can do it. Let's go to open up a data set here. So we've got a data set called charity clustering. So these are uh, individuals who have donated or who have supported a charity in some way. And you can think you can imagine the source of data you have about these people. You have things like the total amount that they have donated. You've got donor ID. You've got whether or not, in this case, whether or not they're male or female. You've got the main channel through which they come. That's quite an important variable here. If I look at that, you can see it's like direct mail, people that have been acquired or interact through events and miscellaneous, people who interact through periodicals, people who use the online channel, the web channel. You've got individuals who got a direct debit with them, and people who have stopped donating when the last year of their donation was. But they may still be on the books, but they haven't donated for a while because, of course, the donor base is changing over time. And if you're creative about this, and you look, very often charities don't have a lot of information about their customers, because they're not selling loads of different products. You might be able to derive new fields. So you might be able to derive fields like here, I have derived fields like how many times have they changed the method of payment? Have they changed it from cash to direct debit? How many times have they changed the amount that they pay? So there's a big difference between somebody who's just inertly allowing a £10 donation coming out of their account via direct debit every month and has been doing that for years. So the amount doesn't change and the method doesn't change versus somebody who has, who interacts with the charity and says, yeah, I've raised some cash here and I'm paying on my credit card this time. I've actually paid on debit card last time and the number of transactions that they've made. So all of these could indicate, something different, something that distinct about these people that makes them different from one another, and helps give the cluster analysis procedure a chance to detect different types of groups. So when you're doing segmentation via cluster analysis, it is a really good idea to think very, very carefully about the types of fields or the types of information you're going to give it, and to give it, data which is meaningful, where you're going to be able to interpret it correctly, um, and which is relatively clean, so it doesn't have a lot of mistakes in it, and doesn't have a lot of holes in the data, doesn't have a lot of missing values, and also where the variables are kind of independent one another, whereas, you wouldn't necessarily expect that tenure would be related to gender and things like that. They'd be different from one another. So if I go to analyze up here, I'm going down to classify, and I'm going to choose a method of cluster analysis. There actually are at least three in SPSS. The one I'm going to choose is two-step cluster. Two-step cluster allows me to use categorical and continuous variables. These are continuous variables. These are number variables. I'm going to put them in there into the continuous variables box. And the category variables like gender, main channel, direct debit, and year of last. Actually, I'm going to leave out year of last donation. I'm going to leave that because that'll be used to kind of do some further analysis. I can ask it to automatically determine the number of clusters. There is a danger of doing that it'll just select two clusters. Let's see what it does. It might only select two. That's because it's kind of optimized. It's actually found five clusters. That's interesting. It's actually optimized towards finding the greatest separation between the groups. There's a little measure called the silhouette measure. You can see it here. And I wouldn't worry too much about not being in the good zone because it's a pretty arbitrary measure, but it's in the fair zone here, so I'm quite happy with that. And it's automatically found five clusters. If you find that it only selected two clusters and you thought, well, I think there's more than there's more segments in there than that, you can simply overrule it and go down to specify the number of clusters. So, but here it's actually selected 5 already. And you can see that it doesn't look like there's much here in the output. It just says there are 8 inputs and 5 clusters. So that's because the output is interactive, so you can double click on it. And if you double click on it, it opens up into its own little cluster viewer. And here in the cluster viewer, I can look at things like go down the model summary here, click on clusters, and it starts to give me a little report on the clusters that it's found. You can see a little chart over here showing me that the clusters are different sizes. There's no reason to believe that they would all be the same size. And you can sort them in order and interact with this. So if I just sort this in order, it'll sort them from cluster group 1 to cluster group 5. Here's our biggest group. Cluster group 5 is the biggest group. And the smallest group is cluster group 3. And we can start to see differences between them. So for example, if I click on this cell here, it shows me that everybody in cluster group 1 is in the no group for direct debit. So that's interesting. This ghost image in the back is actually the overall for all the sample, what the profile is for direct debitors. So it's unusual to find that we've got a cluster here where nobody's on direct debit, whereas in cluster group 2, everybody's on direct debit. So right away, there's a difference there between cluster group 1 and cluster group 2. What about cluster group 3? Well, they're more likely to be in direct debit than not. It's a larger group. What about cluster group 4? Nobody's on direct debit. In cluster group 5, nobody's on direct debit. So the people who are most likely to be in direct debit seem to be, cluster group 2 and cluster group 3. So that's interesting, by the way. What about the gender difference as well? Everybody in cluster group 1 is female. Everybody in cluster group 2 is split fairly evenly. They're slightly more likely to be male than female, even though the overall profile is that they're more likely to be female. Similar situation here, not terribly interesting. Cluster group 4 exclusively male, and cluster group 5 pretty close to the average. So right away we've got something there that makes cluster group 4 different. Let's look at the main channels now. Well, so what we've got is people who don't use direct debit, who are all female, and who exclusively use direct mail to interact with the data. With the charity. Then we've got a pretty even spread in cluster group 2 across the different types of methods it use, whereas cluster group 3 are really heavily biased towards events and miscellaneous. Cluster group 4 exclusively direct mail, and cluster group 5 a lot of people really biased towards periodicals and the web interface. And then we get stuff about the number of transactions. So this is harder to say. You can kind of normalize these views and see where where that lies in relation to everybody else. So you can kind of look at these and say, well, what's that look like when we click on these values here? So you can see down here, but this is quite a low number of transactions, whereas this one here, there aren't as many people in this group, but there's a lot of, there's a lot of people in that small group actually donating quite a lot of money, and the same with total donated and changes the methods. In fact, if you actually select the headers of these and then click on them, you can see it starts to give you a kind of overall cluster view. And if I scroll down the bottom here, it's giving me some little views here. So we can see that, for example, there you go, tenure months. That's cluster group 3. You can see that they're much higher median tenure than everybody else, whereas cluster group 4 only has a tenure of a median of 17.9 months versus 58 months. Same on changes amount. These guys are the most likely to change amount. These are the guys change the most in terms of methods, and these guys donate the most. The median amount donated by this group is £595, and the number of transactions is £33. I think that's because this particular group were raising money um, through charity events. So they're doing things like marathons. They're raising a lot of money, and they're getting a lot of transactions as a result of that, people supporting them. So you get very different groups. So at some point, what you would be doing at this stage is you'd be noting down and kind of building up in your head and discussing with people the different types of clusters and trying to come up with names and ways to describe them. Because if you return to the process, you'd be able to rerun the process again and go to output here And you could ask for evaluation fields, stuff like that, but you could also say, I want to actually save the number of clusters that we're creating here. So actually want you to I want you to create, a cluster membership variable for me here in the output. Click continue and OK. And that basically then creates an extra field on the end telling you, it gives it a very boring name, TSC 6136317, but we can just call it cluster group. And what we'll find, of course, in this variable is that we have exactly the same proportions of clusters that we had in the cluster solution. So you can see it's 25%, 13%, 5.7%, 17.6%, and the largest group, group 5, at 37.4%. Well, you could give them a name. I've actually got a little syntax here that I should be able to open up. Charity clustering. And that just gives them a little label here. So I run this little label on them. It gives me a little label. I could run that again. Did I? Oh, sorry. I've done that wrong. So because of course I've renamed I've renamed the variable. So actually going to run the whole thing again, and that way it's going to be called cluster membership. Just run the whole thing again. There we go. So we've got this variable called cluster membership at the end here. So you can see the names I've attached to these, which are things like key cache femailers and multi-channel direct debiter mid-tiers, solid gold events veterans, key cache mailers, bedrock webfinity mid-tiers. This is typical of the sorts of things that people would use. So you could do an analysis at this stage. You could say, okay, well, I want to do, I want to compare how this has changed over time. And I could say I'm going to do like a stacked bar chart here. I'm going to put the cluster variable into the legend up here. I'm going to put year of last donation along the bottom here. I'm going to ask it to scale it to 100%. And in terms of the chart appearance, I'm just going to choose a different template because I don't like these templates. It's choosing click OK at that point. And what you're noticing is over time the emergence of the solid gold events veterans. So these are people who are starting to emerge. The charity is doing a much better job at finding people who are high value events, money raisers or donors, people who are actually going to take part in charities and events like that. Whereas the other, what's gotten crushed, what's actually getting smaller is probably this key cache femailers group. So we can view how this charity's donor base is changing over time. Now that is called segmentation, and it's obvious that being able to characterize donors or customers in that way can have enormous benefits because it's another way for us to think about the most appropriate ways for us to interact with our customer base, and also to think about how we can move people from one segment to another by studying their behavior. And that's a typical sort of approach that one might take. Now, there is another approach, which is kind of like one might call it Spearman segmentation, which is a really classic way of segmenting data. In our case here, we were segmenting our data by 8 different variables. That's 8 dimensions. But another approach would be to segment them by 3 dimensions. And that's a really classic approach. That is sometimes called RFV or RFM analysis. And the RFM stands for recency, frequency, and monetary. Here we only have 3 dimensions of loyalty. And it's much easier for us to visualize this and how that works because it's a bit like a 3-sided pyramid, where the people right at the top are the people with the highest scores for recent, so they're the most recent. They have the highest scores for frequent, so they're the most frequent shoppers or the most frequent people who do business with, and the highest scores for monetary. In other words, they spent the most amount of money over their time or over the past 3 years or whatever, however you're measuring that in terms of profitability, whatever. And there will be a minority of people who actually score, have top marks in all 3 of those dimensions. The idea being that they are your absolute best customers. And then you can segment them down into, this next tier and the next tier and the next tier. Now, doing RFM analysis is you get something like this: recency, frequency, monitor. You get this typical sorts of output. Um, it's fairly straightforward to do in SPSS. What you'll end up with is a table like this where you'll see a recency score, a frequency score, a monetary score, and then an RFM score indicating this person is in the second tier for recency, the third tier for frequency, and the fifth tier for monetary. Whereas really you want the people you're interested in the people who who are in the top tier across all of these sections, all of these different measures. To do this type of analysis, I'm going to open up a data set here called RFM customers. And I wanted to point out that first of all, I want to point out that I'm going to use a procedure that comes with the SPSS marketing module. I want to point out you wouldn't absolutely need to use this procedure. You can actually do it using other methods like a combination of aggregation and other methods, which are, you could, if you can figure out how to do that, or if you look it up, you'll see that there are other ways to do it. And you'll also point out that sometimes the rows represent individual customers as they do here, but sometimes the rows represent actual transactions. So there's two different ways in which the data can appear. Here, the rows represent actual customers, and I can see that customer one here, I can see this is the total amount of money that person spent. That was their most recent interaction, and that was the total number of purchases that they made, and that's the average purchase interval, which I don't really need at this stage, but that just happens to be part of the data set. Now, if I want to run this analysis and go to analyze down to direct marketing and call up the direct marketing module, and I can do RFM analysis. So this is the direct marketing module, which if you go to analyze down at the bottom, if you see that direct marketing, you'll have this module. As I say, you could do this type of analysis in a sort of manual way using aggregation. But here I'm going to say identify my best contacts using RFM analysis. And when I click on that and select that and hit continue, it says, okay, what type of data have you got? Have you got transaction data where each row represents data for one transaction? Or have you got customer data where each row represents data for one customer? Well, this is aggregated data. It's been aggregated to the customer level by the customer ID. So each row represents only one customer. If I click continue at that point, you can see what it's asking me. It says, what's the transaction date or the interval? So I'm going to say, well, the transaction date is this date field here. What is the total number of transactions? Well, I've actually said total number of purchases here. And what's the total amount purchased? Well, that's amount here. And have you got a customer ID? Well, I've got a customer ID. And it'll pretty much do everything for me up to that point. You can have it segmented in layers of 5. These, I guess, are known as quintiles. Or you could have 10. It would be deciles, something like that, up to 10. So that would be deciles. I'm just going to stick with this. This is the kind of the classic way to do it. And I can ask it to save for me in the output the recency score, the frequency score, the monetary score, and the RFM score, the overall RFM score. If I click OK at that point, it's just going to do that. It goes up and runs that analysis. It gives me a little bit of output. It shows me a heat map here. And it says, anybody up here has the highest value for monetary, has the highest value for recency, and has the highest value for frequency as well. So these three dimensions. There's some other little bits of output here. It shows you how many cases belong in each of these 3 dimensions. But really, the critical bit is here, where we can say, okay, look, here's the recency score, here's the frequency score, here's the monetary score. If I sort this, let's sort this. Let's go to recency and go for most recent, and I'll go for sort ascending. That would be the earliest one. So let's go descending. That'll be the most recent one. This data goes back to 2006, as you can see. So if you're in tier 5, you're the most recent. And if I click here and say sort that in descending order, if you're in tier 5 of the frequency, then you're the most frequent purchases. So the number of purchases that you've actually, 17, 15, 14, 16 here is most frequent purchases. And then monetary, again, if I could sort that by descending order as well. And these are the people who spend the most amount of money. And then we have the RFM score overall. So we can see if I look at this RFM score, you know, how many people actually belong in these different groups. It's treating it as a true number, but you can see you get a score of 555 if I actually turn that into an ordinal field, I think. I just want to see how many people are in the 555 group. Right at the bottom here, well, there's 296 cases in there. There's quite a lot of cases in here too. Look at that. Nearly 40,000 cases. So, but only 296 of them score high across all of them. These are our absolute best customers. And there's another way for us to segment our data and to find the people with who are the most loyal, who shop with us the most and spend the most amount of money. That's another type of segmentation. What else have we got? Well, we've got predictive modeling, of course. Predictive modeling is a third way in which we might work with SPSS to build a marketing application. And predictive methods can include machine learning and statistical approaches as well as AI approaches these days. The predicted outcome normally takes the form of some sort of numerical value like revenue or social media likes or response rates or occurrences over time. Alternatively, predicted volumes can take the form of categories like whether or not somebody upgraded their package or recommended to a friend or whether or not they failed to make a payment or they cancelled a subscription. Depending on the business context, the analyst might choose, this is quite important, analysts might choose accuracy over insight or vice versa. There's two different ways in which you can go with this. If you say, I'm really just interested in creating a model which has the highest level of accuracy possible in identifying people, let's say, who are likely to cancel their subscription or something like that, then that will take you down one path where you'll probably get the highest, the most accurate possible model, but it will be what's known as a black box model, more likely to be machine learning, and it'll be harder to interpret. Whereas if you go down another route, you might say, well, I got much greater insight here because it's a much more transparent model. I can see how it's working, but it means that you may be sacrificing the accuracy. And we're going to choose one which is a lot of insight, does not necessarily the most accurate modeling technique one could use. There are the more accurate techniques, but it certainly delivers a lot of insight. That's the decision tree. But all these methods produce models which generate numerical values in the form of estimates or likelihood scores. And these numeric values empower the business to make selections based on data-driven predictions. So Smart Vision Europe, examples of predictive methods, regression techniques, neural networks you could use. This is all methods you can use in SPSS. Discriminant analysis, decision trees, Poisson regression, survival analysis, time series analysis. These are all linked to little videos that we've done. So if you want to find out more about them, you can click on them, and you'll see a little video about how to make these different types of approaches work. Within direct marketing, it's very important to understand if you're working in a direct marketing application that predictive methods don't exist in a vacuum. They exist as part of a wider process. You don't just apply them to the entire customer base. You tend to be quite selective about it. So in direct marketing, predictive methods enhance existing campaign selection processes. So what you often have is something like global suppression rules, where you say, look, you can't mail these people because they're no longer customers. Or you can't mail these people because, they've said don't mail me. So they're out. And you can't mail these people because we think they're deceased. And then you have people who are eligible for the campaign. You might say, well, this person isn't eligible for the campaign because they've only been a customer for less than 3 months. And secondly, this campaign is actually offers a discount. And some of these customers haven't been profitable enough for us to offer a discount to them, so we're not going to do that. So that leaves you with a pool of people that you would typically then run your campaign against, particularly to your existing customers. And all the predictive model is doing is it's coming along and saying, well, Off that pool of people, the predictive model indicates that these are the people who are most likely to respond. So by creating a model that identifies the most likely responders, we're able to uh, we're able to spend less money targeting people who have a very less than average chance of responding to us. So hence the use of techniques such as decision trees and other predictive modeling methods in in SPSS to do this type of thing. So where do decision trees fit within predictive analytics? Well, they're extremely and extensively and widely used within data science and predictive analytics, and they're used to build profiles of customers and clients and employees. They find behavioral segments because they find groups, and they allow you to generate a predictive model. So decision trees can be expressed as a series of hierarchical rules. So it means that they can be converted into languages like SQL. But they're really popular because they're fairly visual representations of model and and relatively easy to understand. And the way in which we normally introduce this concept to people is we say, well, let's look at the Titanic. And you say, well, what are the factors which led to the sinking of the Titanic or to survival during the sinking of the Titanic? You know, we've got factors like gender and age and class. People are pretty good at guessing what those factors would be. But when you ask them to put them in order and say, what's the most important factor? That's harder, but decision trees are pretty good at that. With a decision tree, it would run a chi-square test and see if whether or not these factors or these variables actually made a difference. Here we can see that female survival rate was 73%, and that gives us a chi-square value with a probability value attached to it. Whereas for adults, survival rate was only 31%, whereas children's survival rate 52%. That's actually a smaller chi-square value. It's not as big a discriminator of survival as gender was. And then we get other ones like the class that they're traveling in. So we can say that, you know, first class 62% survived, uh, third class 25% survived. Yeah. Okay. So we can use statistics to kind of rank or to come up with some arbitrary rank to say that you know, this factor is more important than this factor. This is the biggest discriminator, and this is the next biggest discriminator. So that when we build a decision tree, it's like an upside down family tree. It's basically saying, well, okay, look, we have a dependent variable here, which is the number of people who survived, 711. Then we can put in the next most important factor, which happens to be gender or sex of the of the traveler, of the passenger, and it can continue to grow. Here for the male branch, it says the next most important factor is age, and for adult males, the next most important factor is class. For the female branch, age isn't important at all, doesn't make a difference, but class is important. And it even groups together second class and crew because they're not statistically different from one another. And it means that everybody ends up on one of these final, what we call a terminal node. Everyone ends up in one of these little boxes at the end. Let's have a look at how we can apply this to some actual marketing data. Just before that, I want to point out that even if you have continuous variables, like you know the amount of money people spent with you, as we did with RFM analysis, it will actually just group those values into tenths and then create automatic groupings. It's very good for finding the threshold. Let's say you're offering a discount or something like that, the threshold at which somebody converts to a subscriber or an unsubscriber, or when a bill price increases, at what point do they say, okay, I'm going to cancel my subscription? Let's take a look. So we'll just jump out to SPSS again. We'll go open up a data set. So I've got simple subscriber churn here. I've got charity clustering finance. I'm actually going to use finance. This is a little data set here called finance trained. It means for training a data set. This is a supervised technique, not an unsupervised technique, because we have a variable, a target field that we're interested in. Let me just get rid of some of these other outputs. And if I jump along to the end here, you'll see that we've got this data set, which is, you know, did they buy this product, which is the Super ISA? We ask for some analysis on that. It's 55% didn't, 45% did. So it's a nice, easy example for illustrative purposes. And if I go to build my decision tree, I can go to analyze and I can go down to classify and down to tree. And then I choose my key variable, which would be, did they respond? Did they cancel the subscription? Did they churn? Did they recommend us to a friend? Did they renew a contract? We can pick up all the other variables and send them across, and then ask it to build a tree, choosing the most important variables that discriminate between people who bought the super ISA and people who didn't. Now, at this stage, we have a quite a small data set here of only 300 cases. So the tree is going to be really small, but I'm going to build it first of all, and then introduce you to it, and then we'll go back and see if we can build a more complex tree, one that goes a little bit deeper. But if I click OK at that point and run it, you can see it just built a really, really simple tree. And we can have a little look at it. Let's just zoom in. So far, this tree has only produced four groups. You're either in that group, that group, that group, or that group. So, and it's saying the single biggest discriminator between people who bought super ISAs and those who didn't was the number of children they had. I can actually change the labeling here to make it a wee bit easier. So this group is zero or less. People who have no kids, 35% bought the super ISA. People who had higher than zero but through one, that means one kid basically, 85% bought the super ISA. And higher than one, only 32% bought the super ISA. So this is like a non-linear relationship. Now, there's 110 people in the more than one kid group, and it actually finds that it could split that again. It says, well, if the person respondent is older than 41, then 54% bought it. And if they're less than 41, then 12% bought it. And the reason it's stopping here is because it's getting down to such small numbers. It's not allowed to go any further than that. So we can overrule that and we can say, well, look, let's just go in and say, look, I'm going to give you, for the sake of argument, I know it's a very small data set. I'm going to allow you to go down to a group size of 10. That's the child node. That's these little final boxes here. The parent node being the box where it splits, above it where it splits. And you can see now it's a little bit more complex. We can zoom into it. And just zoom out a bit. So here it's again, it's saying the most important factor is number of children, but now it's saying if you got zero kids and you're married, then 19% buy it. But if you're not married, then 68% buy it. So there's some differences there. And if you're not married and you're not a mortgage customer, then 93% buy it. So we're finding some big differences here between people who buy the product and people who don't. And over here we have estimated disposable income. So it's actually to split disposable income at this key point here. It said, look, if you've got more than one kid and your disposable income is greater than 14,724, then 91% of the people offered the product actually bought that product. And at this stage, you can end up with quite a complex tree. So you're really interested in these segments that it's finding and finding out which segments are the best, which ones are the worst. Where should I be targeting my efforts? If I go back to this, I can click on Decision Tree again, call up the dialog and tell it what category I'm interested in. This is the target category. That's yes. If I click OK at that point, it will produce an extra piece of produce an extra piece of output for me called a gains table. And you can even add in things like costs associated with offering people, and you can put in extra plots and gains plots and stuff like that. There's lots of extra stuff you can do here, but I'll just run with that at this stage. The gains table here is saying, look, these are all the nodes. The nodes are just the boxes that people end up in here, and these little nodes here. And we're interested in which one's the best nodes, which one's the worst nodes, which ones should I be targeting. And it's saying, well, look, node number 15 is your best one. Why is that? Well, because um, you got a response rate of 100% in that. Everybody in that node bought the super ISA, and that node represents 37 people who bought the super ISA, and that is 27% of all the people who actually bought that product. So if you selected node 15 and people fall in node 15, you'd stand a very good chance of having a much higher than average conversion rate. Next best is node 10. That has a response rate of 93%. This index value here is just saying that, by the way, if you get an index of 200, it means you're doing twice as good as average. Whereas down here at node 13, we only have a percent response of 7 point, we have a percent response, I think, of 7.4%. Oh, sorry, 40%. 40%. And that's actually worse than average. So the value, index value is less than 100. If it was equal to 100, it'd be exactly the same as the average. So we really want to select people in 14, 9, 10, and 15 because these are the people who have the highest likelihood of response. This chart here is just telling us how many, what percentage we could gain from different percentiles of the data. So we could find 80% of the respondents from 40% of the data. And a little chart, a little table here telling us how accurate the model has been. Now, really, what you do is you do a lot more testing at this stage. And this is quite insightful, tells me a lot about what's going on. I'd really want to test out the model a bit, but at this stage, I could go to the decision tree and I could save it. I could say, tell me what node number they're in, tell me the predicted value, and tell me the probability. And it would create new data set for me, telling me what node they belong to and what their predicted value is like to be and what's the probability of being in that value in that node. So predicted value here of let's see, I think it's yeah, 2 is yes and 1 is no. So it's saying predicted to be a 2, predicted to be a yes. Now obviously in this case we actually know the responses, we actually know what's happening here. So if I wanted to apply it to a different data set, I'd need to save the model. One way in which I could do that is I could just save the model like this, and I could say, this super ISA, I've actually done it already. Save the model away, and say, yeah, do you want to replace it? Click OK. Then open up my new data set where, the people haven't been offered the product yet. That's called a scoring data set. They haven't been offered the product yet, so they haven't been offered the super ISA, so we don't know if they're going to respond, and we want to know who we should be spending a lot of money on contacting. To do so, we go to utilities, we go to scoring wizard, and we call up super ISA XML model, which we saved away, and we basically run that. And let's see, I just simply tell it. The one I'm interested in is product two. I'll just say this is what I want you to do. Click finish, and it tells me in this new data set here which ones are likely to be in the two category, which ones are likely to be in the one category, and what their probability is associated with it, and what node number, what segment they belong to. So that's how we might use a algorithm, like a decision tree, to build a predictive model. Okay, that pretty much takes us to the end now. Just before we finish up, just you should be aware that we have now in Smart Vision, we have our own chatbot or AI chatbot, which we developed ourselves called Chat SPSS. You can sign up for it yourself and interrogate it and ask it questions about statistics and about how to work with SPSS. It's actually just trained against all of the official IBM documentations on SPSS procedures. If you want to know how to do this yourself, by the way, we kind of did it as an example to show people that this can be done and that they could do this with their own documentation. We will have a forthcoming webinar coming up that shows you how we built this and how we might be able to help you do the same thing. As a result, we of course have a lot of decades of experience in providing training and consultancy in the delivery of data science initiatives and statistical analysis. And that means you can buy your analytical software directly from us, often with discounts. You can buy SPSS directly from our web store. You can switch your licenses to us if you're with IBM. You can switch your license to us and we can look after it for you, as we're experts in this area. We can offer no strings attached technical and business advice, ticketed technical support services, and a range of training and consultancy services. I do hope you found that useful. We will have more webinars coming up in the new year, so you might want to check those out. Thanks for logging in for today, and we look forward to you logging in again in the near future. Thank you.